Let's look at some math regarding the CSTR, continuous reactor systems. So just to recap, this is when you have, this is the basic mass balance, and this is when you have the Nicholas-Menten consideration, and this is when you have biomass consideration, and in terms of substrate and in terms of biomass. So let's look at this first math. A 5 meter cube fermenter is operated continuously with feed substrate concentration 20 kg per meter cube. So you have that. The microorganism cultivated in the reactor has the following characteristics. Great. So we have a lot of data, and we have the yield. We have another information. So what feed flow rate is required to achieve 90% substrate conversion? So somewhere around here we are getting 90% substrate conversion. So if 90% is converted, only 10% will come out. And so if we know SI, we know S. Great. What do they want? They want the feed flow rate. They want the F basically. So we have a lot of data. So also we know that F by V is the opposite of tau, which is D. And our governing equation, this one is very simple. You just use this governing equation because substrate we don't need. Yeah, you can do, I mean, you can use S and then KS and all this, but this comes from here, so this is the most simple thing to use. And let's go for the very simple thing. Mu is equal to D is equal to mu max S by KS plus S. Yeah. So we know the S coming out is 10% of SI. So the S coming out is going to be 10% of 20, which is 2 kg per meter cube. Okay. And so we know S, we know mu max, we know KS, and we know S. Can somebody do the D? Figure out what is the D? Like I said, we know mu max, we know S, we know KS, and we know S, and we know the D. So simple stuff. Figure out what is the flow rate. Okay, and try this at in your own pace. Okay, the first one is pretty simple. Now for the second one, how does the biomass productivity at 90% substrate conversion, which we just did? So we know that we'll just use this D, which is 0.32. And we know the F. If you want, use F if you think that is more relevant. Compare with the maximum possible. So what did they just say? The biomass productivity at 90% conversion. Now we are having some sort of conversion, but that may not be the maximum possible because we have a separate equation for our optimum dilution rate. Okay, so let's look at that. Let's figure out the D optimum, which is related to the QX max, because if this is Q by D, okay, so we are somewhere in this region, probably this D. Okay, because if we go beyond this, it's going to be not optimal. So let's keep that in mind for the next math, the math 2, which I'll give in a separate video. So just keep in mind that the optimum D, or the optimum flow rate, is not always related to the best substrate conversion. So in here you have maximum biomass productivity occurring at D optimum. Okay, and that is a simple formula, not a simple formula, the formula that we derived, and the formula looks like this. Sorry. get it a little bit here. D optimum is mu max 1 minus ks divided by 1 minus root over ks by ks plus si. Let's just write that. D optimum is equal to 1 minus root over ks divided by ks plus si whole bracket mu max. Okay, so what is mu max? Mu max is 0.45, 1 minus, and you have your ks. So basically you don't even need this part A for this part B. You have your ks, you have ks, and then you have si. So given a certain initial substrate, this is your D optimum. What was the D that we got in our part A? It was 0.32, and here we are getting 0.36. Like I said, so some percentage conversion is occurring, but that might not be the maximum that you can get. So if you increase D to up to this point, that means you can still maybe get maybe 95 or 96. I leave it up to you to use this D and figure out what is the conversion, substrate conversion. Okay, and we can talk about that. We can discuss in live class.